Okay, we're going to talk about determinants. The determinant of a matrix is just a scalar value that is associated with any square matrix. So we only talk about the determinant of a square matrix. The notation is det of A, or sometimes you see it with A, looks like absolute value of A with the vertical bars around A. We've actually already seen the determinant in the 2 by 2 case. If we have A, it's just this generic matrix A, B, C, D, then the determinant of A is A times D minus B times C. And we've seen that because we saw that in the a little formula for the inverse of a 2 by 2. So remember, we multiplied by 1 over AD minus BC, so we're multiplying by 1 over the determinant of the matrix, and then we kind of rearrange the terms and negate a couple to get the inverse of a matrix. So notice that at least in the case of a 2 by 2 matrix, we can see that the inverse exists when the determinant of the matrix is not equal to 0. Here in this case, if AD minus BC is equal to 0, then A inverse does not exist. And it turns out that this is true for any square matrix. If the determinant is not equal to 0, that means the matrix is invertible. And if it's invertible, then the determinant is not equal to 0. So this is actually another installment in the invertible matrix theorem, okay, which we had from section 2.3. So determinant of A not equal to 0 is logically equivalent to A is invertible. Alright, if we move up beyond a 2 by 2, there's no nice formula for computing the determinant like there was for a 2 by 2. And we use a method called cofactor expansion. And this method works for any size matrix, 3 by 3 on up. In this method, we have to choose a row or column to expand about. Okay, that's what we call it. We're going to choose a row or column to expand about. And you'll see as we go on that it's advantageous to choose a row or a column that has the most zeros in it because that eliminates some of the terms. But for our first cut here, I'm just going to expand about the first row. And I've kind of color-coded this to make it easier for you to see where the terms come from. Okay, so if we expand about the first row, we start with the first entry, which is the 5, and then we multiply 5 by the determinant of the matrix that you're left with if you eliminate the row and a column that contain the 5. So if you eliminate the first row and eliminate the first column, then you see that you have this little 2 by 2 matrix that's sitting right here. Okay, and so we're going to take the determinant of that. And then we move over to the next entry in the first row, which is a 2, and we multiply that by the determinant of the matrix that you get if you eliminate the first row and the second column. Okay, the row and the column containing the 2. So we're left with the 0, 2 here, and the negative 5, 7 here. Okay, so that's how we get this matrix here. Then we continue moving across the first row. Then we got a 4, and we multiply 4 by the matrix that you get if you eliminate the first row and the third column. Okay, eliminate the row and the column containing the 4. So you're left with this little 2 by 2 here, 0, 3, 2, negative 4, and that's what we have here. Now notice I haven't combined these terms at all. I've just written them out here. And that's because there's a method for combining the terms. Okay, we have to put them together somehow. And basically you apply a coefficient to each term, which is -1 to the I plus j, where I and j are the row and column indices corresponding to that term. So if we look back up the 5 came from row 1, column 1. So the coefficient that we put in front of that term is -1 to the 1 plus 1, because 5 came from row 1, column 1. Alright, then for the next term, this one, the 2, the blue term, came from this entry here. The 2 is in the first row, second column, so that means the coefficient here is minus 1 to the 1 plus 2. Row 1, column 2, that's where the 1 plus 2 comes from. And then for the 4, the green term, okay, it's in the first row, third column, so we have minus 1 to the 1 plus 3 as the coefficient in front of that term. Okay, and so if we multiply and add, then what do we get? We get minus 1 to the 1 plus 1, so that's minus 1 squared. So that's just plus 1 times 5, so we bring down 5. And then the determinant here, remember it's just the crisscross, 3 times 7 minus negative 4 times negative 5. So that's what we have here. Alright, then moving on here to the blue, we got minus 1 to the 1 plus 2, that's minus 1 cubed. So that's negative 1 times 2, gives us the negative 2 here, times the determinant, which is 0 times 7 minus 2 times negative 5. Alright, then moving over to the next term, the green one comes from the 4, and that's first row, third column. So that's the minus 1 to the 1 plus 3, which is minus 1 to the 4th, which is positive 1 times 4. And so you get a plus 4 in front of that term, times the determinant, which is 0 times negative 4 minus 2 times 3. Alright, and then combining a little more, we got 21 minus 20 here times 5. Then we've got 0 plus 10, so just a 10 there. And then here's 0 minus 6, so negative 6 there. And we combine and we end up with negative 39 for the determinant of this matrix. Okay, now just a little aside, it's really not necessary to explicitly compute this minus 1 to the I plus j term every time. If you just look, here's a 4 by 4 where I've put as the entries in the matrix just the row index plus the column index. So 1, 1 position, we got 1 plus 1. 1, 2 position, 1 plus 2, and so forth. So if we look at what that is, we end up with these numbers. And remember, we want minus 1 raised to each of these powers. And so you can see, since they all differ by 1, going from one term to an adjacent term, either in the same row or the same column, you either go from an even number to an odd or an odd to an even. So in any case, alternating terms are always going to have opposite signs. And you always start off in the upper left with a plus 1, because that's minus 1 to the 1 plus 1, or minus 1 squared. So you always know that the 1, 1 position is a plus term, and then everything alternates after that. So it's always plus, minus, plus, minus. So if you know the sign that goes with the first term in the row or the column that you're expanding about, then you only need to alternate terms after that, right? So you always have this checkerboard patterns, and you just need to alternate terms based on the sign of the position where you start. So let's look at this matrix again. It's the same one, but I'm going to expand about the second column this time, all right, just for something different. Now, first note that the second column, or the first entry there, is the 2, and it's in the 1, 2 position. So minus 1 to the 1 plus 2, if you want to compute it like that, minus 1 cubed, that's a negative 1. So this is a negative position here. Or you can say, I always know that the 1, 1 position is a plus, so this is plus, the next one over has to be a minus. That's typically how I do it. All right, so we end up with minus 2 times, again, the determinant of the matrix that you get if you eliminate the row and the column containing the 2. So we end up with a 0, 2, negative 5, 7. So that's where we end up with that matrix. All right, then we move to the 3. Now since the 2 was a negative, the 3 is going to be a plus. And we eliminate the row and the column containing the 3. So we're left with 5, 4, 2, 7. And then we move on to the negative 4. So again, if you forget, we'll go back to the 1, 1, that's a plus. Moving over, that's a minus. Moving down, that's a plus. Moving down again, that's a minus. So we're going to subtract off. That's where the minus comes from. Minus -4 times the matrix that you get if you eliminate the last row in the middle column. So we got 5, 0, 4, -5. All right, we compute those determinants. Here we're going to have 0 times 7 minus 2 times -5. Here 5 times 7 minus 2 times 4. And here 5 times -5 minus 0 times 4. And we can simplify. And we end up with -39 again, which we should. Okay, because no matter which row or column you choose to expand about, you should end up with the same answer. All right, let's move on to a 4x4. All right. Now we're going to take advantage of the fact that we've got a row with 3 zeros in it. So I'm going to expand about the second row. And if you notice, the first entry in the second column, oops. Okay, there we go. Expand about the second row to take advantage of the zeros. So if we look, the 0 here is, or go back to the 1, that's a plus position. So we move down, that's a minus. So the first term is going to be -0 times the determinant of the matrix that you get if you eliminate the second row and the first column. So you can see how the first row is going to be -2, 5, 2. That's what we get there. Then we've got these two rows right here as the second two rows. Alright, then we move over to the next entry. Okay, plus here, minus. So this is a plus entry. So it's +0 times the determinant of the matrix that you get when you eliminate the second row, second column. Alright, then minus the next term. So -3 times the matrix that you get if you eliminate second row, third column. And then +0 times the determinant of the matrix that you get when you eliminate the last column and the second row. So that's where all these terms come from. And you can see the advantage of choosing a row with a bunch of zeros, because the red term, the green term, and the orange term all just disappear because they are all multiplied by 0. The blue one, though, we have to compute now a 3x3 determinant. So we have -3 times the determinant of this matrix. So we use the same method, choose a row or a column to expand about. I chose the third row. Okay, so I've got plus, minus, plus. 5's in a plus position. So it's 5 times this 2x2 determinant here. Then move over, -0 times the 1, 2, 2, 5, and then +4 times the determinant of this little matrix up here. All right, and then +0 because this term's multiplied by 0. So you can see that everything simplifies except for this blue part. And we go through and evaluate these determinants and combine terms and simplify, and we end up with -6 for the determinant of this matrix. Now, just stop for a minute here and think about how much more work would have been required if we didn't have any zeros in this matrix. You know, we would have had to done, what we did with the blue part, we would have had to do that for the red and the green and the orange. So we get, this turns into significant work fairly quickly. Okay, it's a recursive method because, for example, to compute a 5x5 determinant, you have to compute 5 4x4 determinants. Now this is assuming there's no zeros in the matrix. So the worst case, for a 5x5, you have to compute 5 4x4 determinants, and each of those 4x4 determinants requires computing 4 3x3 determinants, and each 3x3 means you have to compute 3 2x2 determinants. As you can see, this gets very work intensive very quickly. The amount of work increases exponentially. So clearly this method does not scale well at all. As your matrix gets bigger, the amount of work required increases exponentially. So it's not a good tool nor a good method to use to compute the determinant for an arbitrary size matrix. 3 by 3 is okay. 4 by 4 really turns into too much work unless you've got some significant number of zeros there. Okay, now let's go off on a little different tangent here for a bit, and first define what a triangular matrix is. Okay, a triangular matrix is a square matrix in which all the entries either above or below the main diagonal are 0. Okay, so here are some examples. I've highlighted the zeros in red just to make it clear. The first one here has all zeros below the main diagonal, so we say that this matrix is upper triangular. So all the interesting stuff is in the upper part of the matrix. This next one, the middle one, is lower triangular because all the interesting stuff is in the lower part of the matrix. Everything above the diagonal is zeros. And then here's another one. This one is upper triangular also. And I just want to make it clear that what defines a triangular matrix is that either above or below, or even both, the diagonal, you have to have all zeros. So this one is upper triangular because below the diagonal we have all zeros. Now it's okay to have some zeros above the diagonal or even on the diagonal, but that has really nothing to do with whether this is a triangular matrix or not. This is a triangular matrix because everything below the diagonal is zeros. Alright, so we have a theorem that says if A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal of A. Okay, so this is making it easy to compute the determinant if your matrix is triangular. Okay, it's pretty easy to see how that works. If we take a triangular matrix, then if we were going to compute the determinant directly, then I would expand about the first column. So my determinant would be 1, that's plus. So 1 times the determinant of the matrix that you get if you eliminate the first row and first column. So you got this 3 by 3 that we take here. And notice that all the rest of the terms would be 0. So it's 1 times this determinant plus this 0 here times, or actually minus this 0 here times another determinant plus this 0 times another determinant minus this 0 times another determinant. So the only term that's non-zero is the one associated with the 1. So that's the only one I've written here. And then if we take the determinant of this 3 by 3, notice we do the same thing, expand about the first column. So we've got 1 times 5, because 5 is in the 1, 1 position. So that's a plus. So 1 times 5 times this 2 by 2 sitting right here. And notice again, all the other terms in that column are 0, so we don't need to worry about them. And so we end up with 1 times 5 times this determinant. And so it's going to be 8 times 1 minus 0 times 9, so it's just 8 times 1. So our determinant's 1 times 5 times 8 times 1, which you see are the entries on the main diagonal. So if your matrix is triangular, life is good, life is easy. Just multiply the entries on the diagonal. Just thinking ahead just a little bit, notice that a triangular matrix is in echelon form. Or if it's upper triangular, it's in echelon form. If it was lower triangular, we could swap rows. And we'd have to swap some columns too, but let's just think about upper triangular at this point. Now, so something to think about. To compute the determinant of a large matrix, let's just say large is 4 by 4 or bigger, could we first put it in echelon form and then just take the determinant by multiplying the diagonal entries? Would that work? Well, to answer that, we need to explore how elementary row operations affect the determinant of a matrix. Okay, so if we can nail that down, then it is indeed possible that we could just put our matrix in echelon form and then easily compute the determinant that way. So that's what we'll ponder, and we'll discuss that in the next section.